so models of specificity, right? The original idea was scientists sort of thought it was lock and key, right? The ligand fits perfectly into the protein binding site, like a key fitting into a lock. It had a couple assumptions. The protein structure was very rigid. It actually made inhibitor design really straightforward. Just make your inhibitor or your drug look exactly like the ligand, in shape, in residues, super easy. Okay. Then in 1958, there were some scientists who won a Nobel Prize for describing this situation, which is something called induced fit. Your book describes it like this. It essentially describes it as like a hand fitting into a stretchy glove. That essentially when a ligand comes in to bind, the protein is going to manipulate its shape to receive that ligand, okay? Stretch to fit around it or whatever it might be. So binding sites have plasticity. They can alter their shape to accommodate a ligand that's coming in. And the problem with this is it makes inhibitor design much more difficult. Because basically, if a protein can change its shape in order to accommodate an inhibitor, so can a bunch of other proteins lying around. They'll also change their shape to accommodate the inhibitor, and what ends up happening is lots of unwanted side effects, right? Because you've designed a drug that can weasel its way into a lot of different protein binding sites potentially. So conformational changes in drug design are really important. So when we talk about kinases again, all active kinases, active meaning they're switched on, right? They're in a conformation where they're ready to bind ATP and phosphorylate something else, right? All active kinases kind of are going to look exactly alike because they all catalyze the same reaction, this phosphate transfer reaction, and so chemistry sort of dictates what that has to look like and how that has to happen, okay? So kinases are all generally going to look the same when they're in an active conformation and they're actually participating in this phosphorylation or this phosphate transfer. But when a kinase is sort of switched off or inactive, it's not receiving ATP and it's not going to participate in this type of chemical reaction. There's a whole slew of conformations it could possibly be in that are all sort of slightly different. And so what makes imatinib or Gleevec particularly clinically effective is because it targets one of the inactive conformations. So ATP doesn't really want to bind that inactive conformation anyway. So Gleevec goes in, binds it, and then that one never becomes active to begin with. It never ever switches on. And so that's sort of, because imatinib is able to distinguish between these like very similar conformations, they're close, but they're not exactly the same. And so that's sort of what's shown here. So this is the active form of a tyrosine kinase, and it has this loop, like this loop linker region here, okay? And so the inactive form, this is the active form. The inactive form that imatinib binds, there's like a little, it's hard to see, there's like a forward arrow here and this backward arrow here. This is representative of like a beta sheet. So there's a slightly different structure to the binding site that imatinib particularly targets. Okay, and so when it binds this form, it never actually gets switched on. And that's what makes it so effective. So conformational changes at the ATP binding site. Recall that ATP binding is the normal, ATP is the normal ligand for this situation. Okay, so looking at this figure, what does the ATP binding site look like? What's going on in here? This is a question for people to shout out an answer to. What do you see?
It seems rather varied.
Varied?
Varied.
Varied? That's the next answer. You're jumping to literally the next question, but why would it be varied? What do we vary usually? Hydrophobic residues. So there's these methionine, valine, alanine, leucine, phenylalanine. These are all our hydrophobic residues. Okay? They're not normally charged. They're not polar. They don't participate in that stuff. So the ATP binding site has a lot of hydrophobic residues in it. So Jay already got the answer to this one. Where would this be located within the protein? It would be deep in the interior, away from water. Okay? Wants to be protected. I think I answered this last time, but we'll bring it up again. So does ATP bind and dissociate really rapidly? So the answer was yes. It happens actually several times a second. So the question is, how is this possible, given that its binding site is so deeply buried in the interior of a globular protein? And so the answer is sort of what is sometimes referred to as dynamic breathing motion, or the ability of the protein to sort of literally open and close itself to receive ATP. And this is, again, an example of this conformational change to allow for ligand binding. So the ATP concentration in cells needs to be relatively high, okay, because it's participating in a lot of energetic reactions. It's sort of the driving force for many things as our energy currency. So it's decently high. It runs a lot of processes, so we expect ATP concentration in cells to be in the millimolar range. Okay. What does that mean for KD? We said that physiologically relevant concentrations need to be near KD, okay, in order to have on-off functionality. Anything higher or lower would always be bound or always be unbound. We know ATP needs to bind and dissociate readily. So how is its affinity? It's not great. It is in the micromolar range, which we said is kind of our lower. It's 10 micromolar approximately, so it's kind of on the pretty bad end. What does this mean for cancer drugs? Our kinase inhibitor drugs? It's pretty easy to design them so that they can compete off ATP because ATP doesn't really have very strong affinity, so you can make a drug pretty easily to kick ATP out of there. It's not that hard. Okay, a good inhibitor doesn't need very high affinity to displace ATP, and the ATP binding pocket has a lot of hydrophobic residues, so in order to increase affinity, you can also kind of exploit that factor. Put a lot of hydrophobic residues on your small molecule, on your lead compound, in order to increase its affinity and easily displace ATP. So here's an example. Here's ATP binding in the Abl kinase. Right? It has a Kd of about 10 micromolar. The change in free energy upon binding is about negative 30 kilojoules per mole, and this interaction features 8 hydrogen bonds. Okay. Gleevec, on the other hand, has a Kd of about 10 nanomolar. Okay? The change in free energy upon binding in this case is more like double, right? So it's much more likely that this interaction will occur than for ATP to bind. It's more energetically favorable to release more energy. And then in this case, we have only 4 hydrogen bonds. So we've taken away some of the specificity and replaced it with additional hydrophobic residues in sort of a trade-off. Okay? So kind of the thing to memorize here, high affinity is achieved through hydrophobic contacts. Specificity is achieved through hydrogen bonding, polar interactions, or charged interactions.